Serial dilutions and titers. Serial dilutions are used when large dilutions are needed. So for this example, what is the final dilution following the sequence performed dilutions? So we do a 1 to 2 dilution, then a 1 to 5 dilution, then a 1 to 5, then a 1 to 10. Well, we would multiply them all together. So the 1s are just multiplied across to stay 1, and then we would do the 2 times the 5 times the 5 to get the final dilution of a 1 to 500 dilution. There are certain pieces of equipment that need to be calibrated using serial dilutions. So we need a value at predictable levels that increase or decrease predictably so that we can evaluate patient samples based on this standard curve. So when we perform serial dilutions, usually what it means is we piggyback off of the previous dilution. So we'll perform a dilution, we'll take that diluted substance or that diluted solution and use that as the solute for the next dilution, and we kind of piggyback them from one tube to the next. So example 2, a sample with an original glucose concentration of 750 mg per deciliter went through the following serial dilution: a 1 to 10, a 1 to 5, a 1 to 2, and a 1 to 25. What is the dilution factor? Well, we would just multiply all those dilutions across, and we would get 1 in 2,500. So what is the concentration of the final tube? You would just multiply our original sample by that dilution factor. So 750 mg, when we multiply it by the dilution factor of 1 to 2,500, you now see that it's actually a division problem. So that's how we got to the 3 mg per deciliter. This is an example of a serial dilution that we perform to evaluate colony counts from an original culture. So if we have an original concentration in here, what we would do is we would fill up the tubes with the solvent, and then we would take the solute or the original solution that is meant to be diluted, and we would mix it. So in this example, we're performing 1 in 10 dilutions, or 10 to the negative 1 dilutions. So what we would do is we would fill each one of these tubes with 9 milliliters. And then we would transfer 1 ml from the original stock into this first tube to get to a total volume of 10 mils. Then from this tube we would mix it up, and this would be another 9 mils, 9 mils, 9 mils of the diluent. And then we're going to take from this tube, transfer 1 mil to the next tube. So basically we are just piggybacking on to make it more and more dilute to the point where we can no longer detect Alright, so you need to create a protein standard curve using serial dilutions. Your original stock of bovine serum albumin is 2 mg per mil. So we're starting with 2 mg per mil. How many 1 to 2 dilutions would you need to obtain a 0.001 mg per mil solution? What volume of sample and diluent would need to be added to each tube? So if we're performing 1 to 2 dilutions, that means that there's 1 part sample out of the entire solution of 2. So if the whole solution is 2 and 1 part of the 2 is the sample, then the other 1 part of that 2 is going to be the diluent. So we get 1 part of sample, 1 part diluent. So in this example, since we're dealing with mils, we would probably say 1 mil of the sample is added and 1 mil of the diluent is added, which the diluent's usually going to be like water, so we'll just put water in here. So that's how much we're going to add to each tube. So we have original stock tube of 2 mg per mil, And if we perform a 1:2 dilution, what that means is that we're going to fill up this first tube with 1 ml of the water, and then we're going to add 1 ml from our stock into the tube. So it'll fill it up so that there's 2 parts total. 1 part out of the 2 parts is the sample. When we perform a 1:2 dilution, we're basically taking the sample and cutting it in half, because 1 part is the dilution or the diluent and the other part is the sample. So in our first 1:2 dilution, our concentration in this tube is now 1 mg per ml because we've cut the 2 in half. So we have to do it again. We're going to perform another 1:2 dilution, and when we do it this time, we're taking that 1 and dividing it in half to get 0.5 mg per ml. And we're going to do it again. Another 1:2 dilution. And we're going to take the 0.5 and we're going to get to divided by 2, 0.25. Another one, 1:2, 0.125. Another one, another 1:2 dilution, divided by 2 is 0.0625. So we're going to have to do another one. And now we're at 0.03125. Perform another one. We got 0.0156. Do another one. And we got 0.0078. And we'll do another one. 0.0039. And we got to do another one because we're not quite to the 0.001 yet. And now we're at 0.00195. And we typically want to take it a step further to get it beyond what we were originally looking for. So we do one last one, and we end up with a final of 0.000976, which can then be rounded to 0.001. So how many 1:2 serial dilutions would you need to obtain that concentration? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 serial dilutions. So here's another example. Your original stock of HCl is 3 mg per ml. And now we're performing 1 in 10 dilutions. So in a 1 in 10 dilution, we have a tube that is 1 part, so 1/10 is the sample, and the rest of the tenths is the diluent. So if we use mils again, that would mean that 1 ml is the sample and 9 ml is the diluent. Why is it not 10? Because 10 is the total solution. So 1 out of the 10 is the sample. The remainder of the 10 is the diluent. So in each tube, we would add 9 mils of the diluent, and then we would carry over 1 mil of the sample from the original stock. So we'll get started on drawing out our serial dilutions. So if we do a 1 to 10 from here to here, that means we would fill this up with 9 mils of the diluent and 1 mil of sample from the original. A 1 to 10 dilution would cut this in half by 10, or divide it by 10. So we would do 3 divided by 10, and in this tube we would have 0.3. Now if we do another 1 in 10, that means we would take 9 mils and then plus the mil from the previous. So this is another 1 in 10 dilution. And if we divide it by 10, now we get 0.03. And we'll have to do another one because we're trying to get to this final number. And this is really what you have to do, is draw them out and then report what the numbers are under the tubes, so you know what the concentration of solution is in each one of the tubes. So 1 in 10, we have a 0.003, and we'll do one more. To get to our 0.0003. So we talked about what volume of sample and diluent would be needed. How many serial dilutions would we need? Well, we needed 4. 4 1 to 10 serial dilutions to get to where we need to be. You have a stock of 12 molar hydrochloric acid. You make 5 1 to 3 serial dilutions. What is the final concentration of HCl? Well, we have to draw it out. So there is math behind this, and you can start trying to do calculations, but it's better always to just draw it out. So this is our stock that we're starting with. And we're going to start performing 1 in 3 serial dilutions. In a 1 in 3 serial dilutions, we're basically dividing it by 3 every time we go to another dilution. So in our first one here, 1 in 3, 12 divided by 3 is 4. Or sorry, yeah. So we now have a concentration of 4. So we want to get down, we need to do 5 1 to 3 serial dilutions. So we are going to, this is 1, 2, 3, 4, 5. And each one is a 1 to 3. So 4 divided by 3, 1.333. Divided by 3 gives us 0.444. Divided by 3 gives us 0.148. Divided by 3 one more time, 0.049. You have a stock of 10 molar sodium chloride. You make 2 1 to 10 serial dilutions, followed by 2 1 to 2 serial dilutions. What is the final concentration? Let's draw it out. So we're starting with 10 molar, and we're going to make 2 that are 1 to 10. So we would take our original 10 divided by 10 to get to 1 for the concentration of this one. And then we would go from here, do another 1 to 10. So divide that by 10 again. And we get to 0.01, or 0.1, sorry. And now we got to make our 1 to 2 serial dilutions. So when we go to a 1 to 2, we're just cutting it in half. So divided by 2, 0.05 in a 1 to 2. And we're going to do the second 1 to 2 that they requested, which means we'd cut it in half again. So 0.025. This is our final concentration after performing those serial dilutions. So just briefly about titers. A titer is a measurement used to express the concentration of substance, usually antibodies, viruses, or cells in a solution. It tells you the highest dilution of a sample that still produces a detectable reaction. So if we want to test if someone has antibodies against a particular virus, like hepatitis B, you've probably heard of getting an antibody titer for a hepatitis B vaccine status. All healthcare employees typically have to be vaccinated against hepatitis B. So to prove that you still have enough immunity against hepatitis B, they want to look at your antibodies to see if you have enough circulating antibodies to be able to protect you in the event that you have healthcare or on-the-job exposure to hepatitis B. So what they'll do is they'll set up a titer for you. So they'll put your sample in serial dilution. So they're going to take the patient sample and serial dilute it down and down and down and down and down. And then they're going to have reactants inside of the titer that, if it's positive, it will turn colors in the presence of antibodies. At the cutoff point where you no longer see detectable reaction, that's considered the patient's titer. So here you can see once it's been diluted, at this point is the break point where there's no longer a reaction. There are set standards for what number the titer should be. So we use those set standards depending on what we're looking for. Every item we're looking for has a different number or cutoff that we would expect to have. So common context for titer use: serology, so like I just mentioned, measuring antibody levels in the blood; virology, measuring virus concentration, so like hepatitis or HIV is a virus that we would want to know if we have viral load increasing or decreasing; microbiology, estimating bacterial concentration; vaccination testing to see if someone has immunity; antibiotic testing to see if the antibiotics are going to work. So how it works: serial dilutions of the sample are prepared. Each dilution is tested for a reaction, a color change, clumping, or cell death. The last dilution that gives a positive result is the titer. And a titer is expressed as the reciprocal of the dilution factor. So if the last dilution that gives a positive result is 1 to 64, the titer is reported as 64. If we go back to this diagram here, we can see that in this tube, this was the last tube that made that positive result. So if this was our 1 to 64, then our 64 would be our answer. So here you can see another application is antibiotic susceptibility. So there's a certain breakpoint where it produces a different color. So here is the breakpoint. The last tube that produced the color change is reported as the titer. Now this happens to be minimum inhibitory concentration, so that's the minimum amount of antibiotic that will still work against this pathogen. So here can also be reported just like titers. There's broth dilutions that can also be reported. So here you can see at the point where this is the final tube, and when it's the final tube, this becomes the titer for minimum inhibitory concentration, the minimum amount of the antibiotic that's going to actually work against that pathogen.